Hello, in this video I'm going to give an overview of the Earth's atmosphere and how it's structured. This is useful because everything that we observe through a terrestrial based telescope has to have travelled through the Earth's atmosphere, whether it's visible light, whether it's radio waves or any of the other wavelengths that can actually pass through the Earth's atmosphere. Everything's had to go through it in order to go down to the Earth's surface. Also, it's the thing that keeps us alive. If it wasn't there, none of us would exist. So it's useful to know a little bit about how it's structured. Now, there's no one way of dividing up the Earth's atmosphere, but the most common way is to divide it up according to temperature profile. So whether temperature is increasing or decreasing with altitude. So as the further we get away from the Earth's surface. So I'm just going to run through these 5 different parts of the Earth's atmosphere according to that criterion and just give you the high spots of each bit. Right, so let's start then with a troposphere. So we started here at the Earth's surface, and this is the bit that we live in, the troposphere. I'll get onto the name in a moment. And this might go out to, say, 12 kilometers altitude, give or take. It varies, but say 12 kilometers. And this is where we've got temperature is decreasing with altitude. This is what we are used to on a day-to-day basis. There's snow at the top of mountains. It gets colder when you go up hills. This is what we're used to. So we've got temperature decreasing with altitude. And the thickness of this layer, in fact, all of the layers, varies because the temperature is changing depending on time of year, where you are and things like that. So at the poles, the troposphere might only be 9 kilometers thick. At the equator, it might be 17 kilometers thick. It depends where you are, what time of year and all that sort of thing. As a comparison, for a bit of context, Mount Everest is just short of 9 kilometers. So we're getting all of the Earth's surface inside the troposphere here. It's the most dense part of the atmosphere. We've got about 80% of all of the mass of the atmosphere is in the troposphere. It's where nearly all of the water vapor is in the atmosphere. So we've got nearly all clouds are inside the troposphere. It's where most air travel is. In fact, it's essential really for planes that have got propellers. You need dense air. So you want to be inside the troposphere for that. You don't want to be going into the thin air. Most of the heating of the troposphere is actually coming from the Earth's surface. So the Earth is heated up. The light comes in from the sun, heats up the surface of the Earth. That then radiates back to the atmosphere. So you get these convection currents. So the air heats up at the surface and you get these vertical convection currents going on. And this is where the name troposphere is coming from. If we go to the Greek, you've got tropos, which means sort of turn or mix, that sort of thing in Greek. So this is what's happening here, these vertical convection currents due to heating of the air from the surface of the Earth. So that's our troposphere. When you get up to a certain point, say around this 12-kilometer altitude, this temperature profile of temperature decreasing with altitude stops. You come to what is known as the tropopause, and this is just a thin layer where this temperature profile is changing. Then it switches over to temperatures now increasing with altitude inside the stratosphere. Now the stratosphere is thicker than the troposphere, but it's still not immensely thick. So say we were starting at this 12-kilometer example altitude, then it might go out to 50 to 60 kilometers. That's our thickness of the stratosphere. And it's the name here, we've gone to Latin this time for strato. We're used to strata on various things, and things that are sort of connecting layers. That's what it's getting at with the name of stratosphere. So it's one of these connecting layers inside the atmosphere. And yeah, temperature's now going back up with altitude. So why is this happening? Well, we've got the ozone layer inside the stratosphere. So this is a layer that we've all heard of, but it's not distinguished by temperature profile, which is not why I've not included it in these 5 here that I'm going through in the description. is distinguished by the fact that we've got all this ozone, this O3, which is absorbing UV that's coming from the sun, stopping us getting fried to death. And this is why the temperature is increasing, because the ozone layer absorbs this UV and it heats up. So we're now getting an increase in temperature from what might have been, say, minus 60 degrees C at the top of the troposphere, bottom of the stratosphere. We might get up to, say, around 0 degrees C at the top of the stratosphere. So we're getting back to the sort of temperatures that we're used to on a day-to-day basis. But the atmosphere is much thinner. You can still fly jet planes up here at the bottom of the stratosphere, but you're not going to be getting your propeller planes up there. But you can get jet planes. Right, so that's our ozone layer inside the stratosphere. Then you get the stratopores. You might be stratopores, you're spotting a pattern here, I would imagine. We then go into the mesosphere, and we're back to temperature decreasing. Mesosphere is a little bit thinner than the stratosphere. So say we were starting off at this 55 kilometers, we might go out to 85 kilometers. Meso, we've come across before, mesons. So we've got mesos, again, back into Greek. This is intermediate. Remember, we were using this for the basis of mesons, because mesons have got 2 quarks, our protons, neutrons, such like. They got 3 quarks. So mesons, they were like the intermediate particles, weren't they? So this is an intermediate layer in the atmosphere. Switching back language again, and it's starting to get cold. We might have an average temperature of minus 85 degrees C, that sort of thing. There's not much water vapor around, but what is there can freeze. So you can get these frozen clouds in the mesosphere. These often come up in pictures called I spelled that wrong. Let's write it again. Noctilucent clouds. These are frozen clouds, essentially, that can create a mirror effect around sunrise or sunset. So you get these frozen clouds. If the sun's quite low, the sunlight can bounce off them, and you get these quite groovy pictures that they stick on the BBC every now and again of these noctilucent clouds. But yeah, it's pretty cold there, and there's not a lot going on really in the mesosphere. You then get, surprise, surprise, the mesopause. We then move into the thermosphere. We've now got temperature going back up again. Now, the thermosphere is, if these other layers weren't well defined in terms of thickness, the thermosphere really isn't well defined in terms of thickness. Say we were starting off at this 85 kilometers at the top of the mesosphere. This could be going out to 500 or even 1,000 kilometers. It really depends upon solar activity, is probably the main thing here. There's a lot of interaction between the solar wind and the outer edges of the Earth's atmosphere. This is where we then get the ionosphere inside the thermosphere. We've got loads of charged particles in the ionosphere. Again, I didn't include it in these spheres because it's not defined by temperature profile. It's defined by the fact that it's got these charged particles. This is where aurora occur. So we've got this interaction between solar wind and a very thin Earth's atmosphere. And the very thin Earth's atmosphere means if we're talking, in terms of thermodynamics, in terms of our 3/2 kT, we can get temperatures of up to 1,500 degrees C inside the thermosphere. Really, really hot from a physics calculation point of view. Don't think that this is what it would feel like, compared to, say, 1,500 degrees C in the troposphere, where we've got much higher density. You're not gonna, if you stepped out in the thermosphere, the atmosphere is so thin, you're not going to just fry alive. Okay, you wouldn't be able to breathe because there's not really any air there. But putting that aside, there are so few collisions with the particles in the thermosphere that you're not going to get much energy transfer to you. This is really what we're thinking about when you see the weather forecast and they say, oh yeah, it's 30 degrees C today. we go out in the troposphere at 30 degrees C, we're being bombarded by high energy particles. It feels hot. You go out in the thermosphere at 1500 degrees C, you get hit by one particle or something. You don't burn alive when that happens. So don't get too, don't put this temperature, this 1500 degrees C, into everyday understanding of temperatures and weather forecasts. But still, from a thermodynamics point of view, it's hot. It's thin enough, the atmosphere in the thermosphere, that you can get satellites. We've got loads of satellites orbiting around. Okay, they experience some drag, but not enough drag to make them unviable. The International Space Station, that's also in the thermosphere. That's why you can get such good shots of it through a telescope, because it's not actually that high up. It's still just drifting around, orbiting in the thermosphere. Then we get to the thermopause, and we get into the exosphere. Now, the exosphere is, well, how far does that go out? It's like, well, how long's a piece of string on this one? You need some definition of when an atmosphere ends and when space begins. And there is not one clear definition of when space starts. Do you set some particular density of the atmosphere, but then how do you know what is the atmosphere and what's the solar wind? It's really mixing there, so that's quite difficult. Do you start looking at things like the Van Allen belts? These are essentially the magnetic field of the Earth going out into space. You get the magnetosphere. If you start considering that to be part of the Earth's atmosphere, then that goes a really long way out. I mean, you could be halfway to the moon with that, a couple of 100,000 kilometers. Some people will look at the comparative strengths of the force due to gravity towards Earth, and because that's clearly an Earth's influence force there, the force due to gravity, and then the force due to radiation pressure from the sun. Because if these things start becoming equivalent, and they're very similar in magnitude, well, there doesn't seem to be any reason to prioritize the Earth over, well, being in space or the sun. I mean, that's where the radiation pressure is coming from. So if the force due to gravity is no longer primary at a particular point, then you could argue, well, we're not in the Earth's atmosphere anymore. But it's a bit of an open question where the exosphere actually ends. But we're just getting further out. The atmosphere is getting thinner and thinner. You got a lot of satellites floating around there as well. I think when it comes to astronauts, if you get more than 100 kilometers above the Earth's surface, so if you get beyond the mesosphere, if you've got into the thermosphere, you're considered to be an astronaut. I think that's at least that's what it used to be. I don't know whether they've changed it since then. The only other thing I was going to mention here is opacity to EM radiation. So if we've got our electromagnetic spectrum, so we've got our wavelengths, we've got our short wavelengths here, so we've got gamma going all the way down to radio, then a lot of these wavelengths do not penetrate the Earth's atmosphere. And good thing, as we said with UV being absorbed by the ozone layer. If we get any of these short wavelengths coming through, then everything just burns. So the atmosphere is opaque to gamma rays all down UV. We can obviously see visible light. We can see the stars in the sky. So you get visible light that comes through. You get a little bit at the short end of IR. The short wavelength infrared, a few bits come through, but not a lot. Infrared is mostly blocked. Microwaves mostly blocked. I mean, you get a few little ups and downs, but you're getting small amounts coming through. Then we get into radio waves. You've got a bit with radio waves which might go from, say, 1 centimetre up to around 10 metres, where radio waves can get through the atmosphere, and then the longer stuff doesn't get through either. So, I mean, you would have seen this sort of graph in your textbooks. It's not as blocky as this. It's not just the case of, oh, yeah, these bits get through. You get this sort of wobbly line, don't you? You get the bit that's blocked and then a gap and then sort of, various little wobbly bits. and then the bits of the radio waves can get through as well. But yeah, we've got relatively small amounts of the radiation can actually penetrate the atmosphere. So if we got terrestrial telescopes, these are the only bits we look at, radio and visible. If you want to look at infrared or UV or anything like that, then we need telescopes in space so that the atmosphere isn't getting in the way. And you really see the effect of the atmosphere as well when you're observing how much water vapor is in it, even if it's not cloudy. If you've got a very turbulent atmosphere, it's quite humid and such like, then the stars really twinkle a lot. You get a lot of shimmer. And when you look at things like the moon, you can see the atmosphere moving around, and you can see your both looking through the eyepiece, and if you're taking photos, you can just see all of the blurring that's going on and how you're not getting particularly sharp images. So of course, this is why they stick telescopes in drier parts of the world up the top of mountains. So you go to Chile or Hawaii and things like that, and you want to cut out as much of the atmosphere as possible, and you want to have as little moisture there as possible. You want to have nice still air, still dry air, which is going to make it much better for observing. So that's just hitting the high spots really of how the atmosphere is structured.